Doctor,
We have been looking into the specifications of one of the flat plate collectors. The specification is made by an independent agency, which is located, it will be in the US. This is a German or Austrian company called Weissmann, and it has a factory in the US, like many of them. I mean, there is another very famous, I think it was an Italian company called Califfi, and it has a factory that produces collectors in the US and so on. So what they do is that they go for this independent agency so that they can test and publish the test of their collector. The test includes uh, average values of the kilowatt at different heating temperatures. It provides the dimensions of the unit, the efficiency of the unit, and we see the efficiency here is given a second order polynomial, as you can see from the equations here. One of them is for the SI units, one of the bridge system of units. And what I was asking you to look at here is the value of the intercept and the slope. Because we said last time that there are a couple of ways where we can express our efficiency. The efficiency can be expressed in terms of a straight line formula, as you can see it here, or it can be given as a second order polynomial, as you can see here. This one is a little bit more accurate, but the accuracy of the straight line formula is not bad as well, which many are using it as like recognized values. Dimensions are given, the weight of the unit is given, its capacity of the fluid is given, the test pressure up to 900 kilopascal, which is 9 times the atmospheric pressure, is given. The next page is going to be talking about in details about sort of materials that they are using, the construction details of it, glass sheets, steel, the insulation, and so on. So it has so many further details that are given here in the second page. And then a third page and a fourth page for another collector and another collector and so on. So as I mentioned, what we need to remember from here is are these two values, slope and the intersection. Why I'm asking for this? Because when you look at a figure like the efficiency figure, you may know that we said that the efficiency of the solar collector would look like this. And basically, what we have is sort of a straight line formula. This is basically the efficiency versus T minus TA divided by the solar collector, divided by the solar intensity. So you may see here that we have basically an intersection and a slope. So this is the intersection here, this value, and this is the slope. And these are represented basically by a couple of two values. The slope can be considered which in our case was, let me get the sheet here to see what was the value that we read, minus 5674. Watt per meter square centigrade. Yes, and the slope was 0.044. Normally, when you are dealing with softwares that are related to the solar collectors, they will ask you for these values. What does these values make, or what do they represent? Actually, the slope represents FRUL, which is the heat loss coefficient, and the intercept represents the value of FR tau alpha. And we have seen these values as we are calculating both the dimensionless x value and the dimensionless y value, and how we made use of that to calculate the F factor, which is the fraction of the energy which is handled by solar. So now the thing that we need to consider here is one example. So I just picked up one example from the book, or actually one of the problems at the end of the chapter. And I just thought before I show the problem with you, I'll just show you how the solar collector efficiencies are accounted for. Some people would say they would not take this as a straight line, as an accepted thing, and they may go for something like this, which is a second order polynomial. And that's what I'm saying, that it does not make a big difference actually. When you are going from one collector to the other, you will find that some collectors are having this shape. Let me get into, because we are looking for some sort of a comparison now. So this is basically the efficiency. Efficiency. And here we have basically delta T divided by I. And when we are looking at these values of the efficiencies, you'll find that some flat plates, some collectors will have a shape like this, efficiency curve, and some others would have a shape like this. As a matter of fact, this shape is normally given for flat plate collectors. Whereas this is normally is for evacuated tube collectors. The reason of making this is that it will give us right away some sort of a quick indication. If I'm looking for a small delta T, then I would go for a flat plate collector. But if I need to heat the water or the air, the fluid in general, to high temperatures, then I would select an evacuated tube collector. So that's some sort of a quick look at what would you select. As a matter of fact, there is another, or there is the other thing which looks like this, which is basically the unglazed collector, which is normally used for pools, swimming pools. It is good for small temperature difference, but basically it's limited to this, and it has high efficiency as long as the temperature difference is small. If you need to go for higher temperature difference, it does not work at all. Now let's look at one example. As I just mentioned, the example is considering, let me open it. Oh yes, I think I have it here. Somehow it was not copied, so I'll just have to open it again. Let me see if I can copy the text here. Oh yes, here is it. So this is the statement of the example. I'm just trying to save area as much as I can for the solution. So it's asking for a comparison between two collectors. Both of them are used for heating water for a house. The two collectors are A and B. They are characterized by a corrected slope of the collector efficiency. This is why I started by looking at the specifications of solar collectors and looking at the efficiency, graph of 6.8 watt per meter Kelvin and intercept of 0.7. The system B, the other system, has a different slope, 7.9, and a different intersection of 0.75. Now the question is, which collector system will provide higher energy for a month or across a month, assuming water is to be heated to 60 degrees centigrade? The average outdoor temperature of this month, the month has been selected to be June, so average temperature 18. The monthly solar insolation on the collector is 450 megajoule per meter square. This is the total solar energy falling into the collector throughout the whole month. And the heat is needed, the load. We need the collector to provide 2 gigajoules of energy, and the collector area is basically 5 meters square. Now we have two collectors, collector A and collector B, and we are provided with some information about the collector. And this information basically is in terms of slope and intersection. We'll start by the first collector, A. Slope. Is nothing but FRUL. And this is given to be 6.8 watt per meter centigrade or meter Kelvin. Whereas the intersect it intersects with the y-axis at FR tau alpha, and this is 0.7. There are some information here added that we would like to know, that the outside air temperature is 18 degrees centigrade. This is T air. And we are in the month of June. And the heat load is 2 gigajoules. This is another thing that we'd like to know, and definitely the area is 5 meters square. Now, the equations that we use or that we need for this case is to calculate the value of X and calculate the value of Y. X is basically FRUL. This value is given to us into area of the collector into N. It's a time frame basically. It can be a month. It depends on the data given in the problem. T reference minus T air. This is all divided by the load L. Now looking at this, what do we have and what we don't? FRUL, this is given to us. This is basically the slope, which is the 6.8. AC, or area of the collector, is 5. T reference normally is 100 degrees centigrade. It's a standard value where T8 is 18 degrees centigrade. Fadda.
Yeah, regarding this T air, if I wanted to design for my own house, can I use for the current month, or I take average of the year? Or how
actually, you have to do it for every month.
Oh, I have to do it for every month. Okay.
Remember the example I showed last time that was in Arabic? It is to be done for every month.
Okay, then how I can take the final collector design based on
you are going at the end to come up with an F factor, F value, which says how much of the energy will be taken by the solar collector, and it will give you some sort of a value of the energy like an average value of the energy that you are going to look for collectors. Suppose that you have an energy which is equal to 50 kilowatts, and there are collectors that each one is given something like 5 kilowatts, then you need 10, and so on.
Okay, so the value that I am looking for is the energy. That's it, and then I can give it to the, okay.
Or you can make a shortcut and use a program called Red Screen. It will give you the whole thing right away.
Okay.
It's just the only drawback with the Red Screen is that if you are going to get the free version, you can have a report to be seen on the screen, but you cannot print it. That's all. But you can get the values that you want from that report anyway.
Oh, it's great. Thank you.
Yeah. Okay. Now there's one more thing here that we need to look at. N used to be a time domain. It depends on the units of the system that we have here. L basically is given as joules. And here, this value is watt per meter Kelvin or meter centigrade. This is meter square, which is, sorry, the area is meter square. And it has to do with time. This is Kelvin or centigrade. It will cancel out. This is joule. So it looks like this actually should be the number of days. And at the end, the value of x as it will be calculated, this is supposed to be sort of a dimensionless unit. Sorry, this is watt per meter square Kelvin. So you'll find here that we have watt, and we have here joule. Joule is what? Joule is watt into second. So N here, if we give it as a month, and this is given second, they don't work out correctly. So we have to convert this into seconds. So what I'm going to do here is that the value of N in the calculation of X should be expressed in seconds. I'm talking about a month of June. So 30 days, every day is 24 hours, and every hour is 3600 seconds. So note that as long as we are dealing with watts and joules, then N here in the X expression should be given in terms of seconds. Now, when we substitute, if RUL is given as 0.6.8, AC is 5, N is this large value that will be coming here. This is 100, this is 18, and L is 2 to the power of 9 joules. When you do that, you are going to calculate the value of X, which is going to equal 3, almost, actually it's 3.03 if you want to be accurate.
So Dr. N is always in seconds?
Not always. N is always in seconds if you are dealing with watts and joules in the X expression, dimensionless X expression.
So let's assume it has to be in days. What would be the difference in the F and L?
In this case, L should be given in terms of days.
Yani watts times days.
Exactly. So that, or watts times months, so that the month will cancel with the month.
So it's given in the question as gigajoules. So
yes,
that automatically
that's
will
why
be
I
second.
converted it into joules, and joule is watt second.
So
That's
if it's
here and there's a day here.
So if it is a day, then what will be the formula for the unit for the heat load?
I'll answer your question by this. What's the value of Y? Value of Y is FR into tau alpha multiplied by n multiplied by AC multiplied by the load H T. Divided by Y. Okay, sorry, divided by L. I'm sorry.
Doctor, the formulas in the slides does not show the n.
Because it has been done per a day, and we have only used like 24 hours or something.
Okay.
Here, what did he say in the problem? Look at the load. When we are talking about the load here, he said what? He said monthly insulation on the collector for the June is this. So it has actually 450 megajoule per meter square for every month. So in the problem, he stated that this is given as monthly value, which means that if I need to substitute for the values that I have here, FR tau alpha is going to be 0.75 into n. Here I'm going to take n as equal to 1. AC is equal to 5, and this value is 450.
Shouldn't be 0.7 instead of 0.75?
It should be 0.7, yes. I don't know where did I get the 5 from. Was it for the second one maybe? Yes, sorry. So it should be yes, 7.7. So it's 0.7 into 1 into 5 into, this is 450 into 10 to the power of 6. What are the units here? Megajoule per meter square month. And here we have n is given in months. So this is why I should put n as equal to 1 for this case. And L is the same.
So it needs to be joules per meter square, right? Since we multiplied it by 10 to the power 6.
J, I mean, what we have here is J is joules, just joules. The units will cancel out because the area here is given as meter square. So the meter square will cancel with the meter square. And the month will cancel with the month. So here it is basically converted into joules, and here we have it as joules. We multiply by 10 to the power of 6. So joule over joule, so it's dimensionless. Can you see that?
Yeah, clear, thank you.
Actually, this is the only trick that you need to consider when you are looking at this kind of problems, that the tricks are all related to the kind of units that are being used. Now, if we have the values of x and y, then all we have to do is to calculate the value of f then. The expression that we are given.
I apologize, doctor, for interrupting you, but when we look at the 450, the unit in the question, it says megajoules times meter squared.
No, times meter to the power of -2.
Oh, okay. Okay, sorry.
Yeah, no problem. Minus 0.065x minus 0.245 y square plus 0.0018x square plus 0.0213 y cube. And when we substitute, we'll get a value which is 0.46. What does this mean? It means that when we are using this solar collector, we are going to use the solar energy to cover 46% of the total load. The remainder of the load, which is 54%, is going to be covered by anything else. It could be electrical or diesel or natural gas or whatever heating source needed. And this is why in the program I was telling you about, which is the red screen, it recommends some, based on the F factor that it calculates or the F value, it recommends a certain number of collectors for your system. Then you have the freedom to change the number of collectors. Suppose that you are solving a problem and it has recommended 8 collectors to be used, and it has given you a solar fraction or an F equal to 0.46. You may say, no, I'm not going to use 8, I'm going to use 12. And then the 0.46 here is going to be maybe something like 0.65. Or I say, no, I need to use 16. So what basically you are going to have like a 0.8 solar fraction. It's all up to you as a designer, as a user. The point is, when you are using more solar collectors, then you are going to pay higher capital cost at the beginning. But you may have also longer payback period. But what you are going to pay as a running cost is going to be much less, because you are utilizing more solar energy compared to and less electrical energy or any other fuel. So you are saving in the fuel, you are saving in the emissions to the surroundings, and that's how the economics would be. So actually, a program like that I'm telling you, or just the analysis that we are doing, can provide us with technical feasibility, economic feasibility, as well as environmental feasibility, because the software can tell you how much tons of kilograms or tons of carbon dioxide that you are saving by using a certain percentage of your load given in solar energy. It can give this as tons of carbon dioxide, or maybe in number of barrels of unburned fuel, or so that you are saving, for example, 2,000 barrels of oil per year because of putting this number of solar collectors into a certain building or on top of a building. The second part of the problem is just a repetition. We don't have to do it in details, but what is it doing? It is providing us again with another value of FRUL, which is the second collector, collector B, and this value is 0.7, no, it is 7.9. And FR tau alpha, which is being given as 0.75. What you need to do, take these two values and substitute them here and here. And once you do that, you will be able to calculate what's the value of F here. When you do this, you will get a value of F of 0.47. Difference is not much, which tells that both of these collectors are of the same type. I would assume that both of them are evacuated tube collectors. The problem did not say, and we are not supposed to be calculating the value or estimating what's the type of the solar collector, but from the efficiency curves that I've seen, the solar collectors that are having an intersection of the efficiency of 0.7 or more, this is flat plate collector, whereas the one which is having an intersection of 0.5 is basically an evacuated tube collector. The flat plate collector has higher effectiveness, higher efficiency at low temperature differences, but it has a high loss coefficient. It loses energy to the surrounding at a higher rate. The evacuated tube collectors are having low efficiency at lower temperatures, but it keeps its efficiency. It has much lower coefficient of loss. So why is that? Because we don't have convection heat transfer escaping from the hot fluid to the surroundings for the collector, except for the connections, which is a minor value. So that's why the slope here is not steep for the evacuated tube collector. The evacuated tube collector is this one. So that's what I'm saying. If you need higher temperature differences, then basically you'll go for evacuated collectors. The flat plate collector can be very efficient if you are looking for heating up to 70 or 80 degrees centigrade. But going for 90, 100, 110, 120, then the evacuated tube collector is a better collector in terms of efficiency. Maybe I can give a closure to this example by sharing another file with you. And this file is interesting in the sense that it is showing some sort of a comparison between them. It's some sort of a, I would say it's, how to put it, just to describe it. It's some sort of a generic, which means that the values are not values that you would rely on for calculations, but it's just given an idea of how it would be looking like. How would it be?
بس دكتور في الإكزامبل اللي تو وريتني إياه السؤال. What's the final solution? When I see A, B, C, D.
No, the A, B, C, D, E, these are not questions. They are basically sort of conditions that temperature of the outside air is 18. This is not a question. This is just piece of information that are given in the
Okay. Which one we have chosen? The question was asking between two collectors.
The question was saying which collector would you use?
Yes.
And answer, this is it. For example, compare two liquid-based collectors. This is what he needs, a comparison. So it's basically the F value is what we are looking for this collector and for that collector. And you are going to say which one of them is better. So this one is slightly better for the month of June. Maybe if you tried it for different months, you can get something different so that you can assess it on the overall year. But the ABC here is, A is saying that water should be heated to 60. B is saying that the outdoor temperature is 18. C is saying that the monthly insulation is 450 megajoule per meter square. D is saying that your load is 2 gigajoule. And E is saying that collector is 5, area is 5. So they are not basically needed values.
Okay.
They are just pieces of information that are given to you.
Doctor,
Right?
I have a question.
Yeah.
The FRUL is given as watts over meter square Kelvin, whereas the temperature for reference and air are given in Celsius.
It does not make a difference because it's a temperature difference. The temperature difference, whether it is Kelvin or Celsius, here I can even, for the FR, I can remove the Kelvin and put it at Celsius because it's based on a temperature difference. You know, like when I say that 20 minus 10 is 10. What is the 20? It is 293 Kelvin. What is the 10? It's 283 Kelvin. So it's basically a temperature difference is the same.
I understand, but how can they cancel each other if one in Celsius and the other in Kelvin?
Because it's a temperature difference, and a temperature differences does not make a difference. Both are the same.
Okay.
Okay. There was a file. There's something here. My computer is going crazy somehow. I'm just seeing screens that open, screens that close. I was only wishing to look for one file in.
شكلك ناوي تصعب علينا الاختبار يا دكتور دام السكرين عندك بعد.
لا ده هو بس اللي بيحصل ان السلك بتاع الماوس بيروح على الواكم فبيعمل لنا it opens things which are not needed. مالوش علاقه بالاختبار.
زين.
عفوا I cannot hear you. الصوت بعيد.
اي شابتر الدرس ده؟
اللي احنا فيه الشابتر اللي احنا اتكلمنا عنه يوم السبت اللي فات اللي هو شابتر 11 بيتكلم عن الاكتيف سولار انرجي اللي هي بيزيكالي بنتكلم على السولار كولكتورز، وده اللي احنا عملناه المره اللي فاتت. كان الكلام كله على السولار كولكتور تايبس والاف تشارت ميثود. اوكي.
يعني دكتور في البارت حقك بالنسبة للفاينل اكزام will be the solar collector, right?
It will be the solar energy in general now اللي هو chapters 9 and 11.
مسجل الدكتور chapter 9 and 11.
Yes.
بس
ده اللي
دكتور يعني
غير اللي يخص الدكتور مخيمة.
we will be asked about the collectors but we need to have the knowledge of chapter 9 صح؟
Yeah, chapter 9 you need the knowledge based على الاكزامبلز او اللي احنا عملناه في chapter 9 لو تفتكروا.
Yes.
There was calculations of the values وازاي نحسب قيمة الانرجي اللي نازلة على ميل معين وهكذا. That's something that we have done.
Yes.
chapter 9 يعني بالاختبار دكتور يعني حيجي سؤال منه.
نعم معانا ان شاء الله chapter 9 لان it's an essential part. There is something else here which is it's repeated but it's again I just want you to be used to this kind of data. This again a specification sheet by another company for solar collector. It's called Apricus, and what we see here they are given the efficiency curve right away, and you can see it here. It's a flat plate collector, so we're talking about an intersection of the efficiency which is FR UL as 0.75, and this is the slope. And dimensions are given here. Some of them do not give the intersection and the slope. They just give the equation which is needed for this as a second order equation right away. This is one thing. Second thing that you may notice is there is difference between the way the x-axis is defined in different cases. What we see here, it is simply delta t, and the delta t is Tm minus Ta. Tm here is an average value. It is not the Ti, and this is a measure between the American and the European kind of standard. In the American standard, they say Ti minus Ta. In the European, they say no, we're going to use Tm minus Te. It is something like the famous fight on the units. There are SI units, but still the Americans are keeping their bridge system unit as well as the British people. So you just need to be careful when you are looking at the collector performance curve that it is plotted as efficiency versus temperature difference. And what kind of temperature difference? Or it could be efficiency divided by or efficiency versus the temperature difference divided by I, which is basically the standard. So that was another one. And I think I had another one to show you for the evacuated tube collector kind of solar collectors. And I think I should have it here. Yes. This is another Apricus, but it's Apricus, and you'll see here that the file I'm going to share with you, this file has done by the same independent agency that I mentioned earlier. So you see, it's the same sign, the same logo that we have here to the left, and when you look at it, you'll find that it is providing us with, again, this information of how much is the load per kilowatt, depending on what's your temperature difference. Are you intended to increase the temperature by what value, and the different types of applications you need it for. And it is given, again, the issue of the y-intercept and the slope. Look at the y-intercept here. When we did it for the flat plate collector, this value is something like 0.77. Now, for this type, which is the evacuated tube collector, it is 0.458. So we have a lower slope here, we have a lower intersection, but the slope is much less steeper compared to the other one. And then the rest of the information are being given here in terms of like what is the gross length and the width and the weight and this kind of stuff, and the number of tubes. Actually, the brand here says that it is AP30, so it has 30 evacuated tubes. Oh, this certificate has expired, by the way, because it was issued in 2009 and it expired in October 17, 2020, which means that they should have either uploaded or modified this model to get like a new model, or maybe they send it for testing again. And what other thing you may look like is look at the gross area, 4.16 meters square. The net aperture area is 2.8, but the absorber area is 2.4, because the difference between this and that is that we have tubes, and in between the tubes there are empty areas. These empty areas are accounted for the net area of the aperture, but they are not absorbing areas. And the test has been based on the ISO standards. There was another file still I'm looking for that I hope I can find easily. I was just loading it today. Oh, yes, here is it. The nice thing about this figure is that it shows us to some extent a comparison between the types and when to use what. So it is this kind of figure. It is basically values here are generic, they are not exact, but the point is it will give us the kind of which type of solar collector you can use for which type of application. For example, the one on the top is the non-glazed, which is only used for utilization in solar swimming pools. And the temperatures here, it is talking about temperatures above the ocean temperature, which is like a standard of 25 degrees centigrade. And this is all divided by the solar energy, which is 40 watt per meter square. If you are looking for a very small temperature difference, which is normally you need it for a pool, then that's what you need. You need a temperature that does not exceed 30 to 32 degrees centigrade. So this unglazed type is better. Then if you are looking for a temperature delta T over I up to this value, then it is the flat plate collector which is glazed, having glass on the top. If you need higher temperature differences for heating, then you go for this one. And Abir Mufarraga, which is basically the evacuated tube solar collectors, and you go for that. If the seawater temperature is 50, then you are talking about temperatures that are higher than 100 degrees centigrade. You go for this type of evacuated tube collectors. Whereas the flat plate collectors, the glazed flat plate collectors, from 10 to 50. So if you need to heat from say 35 or 30 up to 100 or up to 90, then this flat plate collector is the suitable one for you. That is all based on the efficiency, because the one you are going to select, suppose that your calculations are to be somewhere here in this area, then definitely you are going to go for the flat plate collector. What if your calculations brought you here? Definitely you have only to go to the evacuated tube collector and so on. So that's some sort of a guideline of the selection of the collectors. Now there is a new collector type that has been added in the last few years, which is a flat plate, but it is evacuated. So it has a performance which is superior to this one, because the area is the aperture area and the net area are the same. And it's not only that, but it has an opening so that every time, with time, I mean, as the time passes, if you lose your effective vacuum, you can evacuate it again. Just open a knob and apply a vacuum pump into it, connect it, and then you are going to restore your vacuum and restore the performance again. This is what the companies have been claiming. I think it has been introduced to the market in 2016 or 17. That's it for as an exercise to this part of the chapter, and that would be it, unless you have questions or something to raise or comments.
Dr. Mohammed.
تفضل.
I would like to thank you for all the information that you have given in this course, but I have a question about the formula sheet. When will be provided?
Yeah, I received part of the exam, and then probably we're left with one question or one problem or so. So once we complete it all, we'll release it. Hopefully over this weekend, we should be able to post it there, inshallah.
Thank you so much. Thank you.
You're most welcome.
دكتور كم سؤال كل الفاينل حيطلع؟
والله still I'm not sure يعني it could be somewhere between 3 to 4 problems or so يا محمد لسه I'm not sure. But it will not be more than 4.
دكتور في multiple choice?
This again I did not talk to Dr. Ismail about this issue. I'm not inclined to put a multiple choice question. I would rather prefer that we have some sort of analysis. But I'll just provide you with this piece of information on the blackboard, hopefully by the end of this week, inshallah, so that you would be aware of what kind of problems that you will see.
إن شاء الله تكون ليلة سعيدة يا دكتور.
إن شاء الله بإذن الله إن شاء الله. طيب يا شباب، أوكي، أشوفكم على خير يا رب إن شاء الله.
الله يسعدك يا دكتور. شكرا لك يا دكتور.
في أمان الله، مع السلامة.